not all that great. So, all right. So everybody got a scratch paper. All right, everybody face this way. What we're doing today is we're starting on stoichiometry, and the lack of handwritten assignments this year, because I've been doing everything, especially this chapter digitally on sampling, is gonna make it more difficult. And so right here at the very end, I want to turn this up a little bit and get everybody writing stuff down so you get used to doing the math, because we're to the point now you're not going to be able to just do this in your head with your computer calculator. You've got to write stuff down. You got to keep track of it. You can still use your computer calculator, but you really need to break these problems up into small little chunks and do one little mathematical operation at a time. Multiply, get your answer, figure out what you need to do next, get your answer, and kind of break it up into chunks. And so every time you do a little bit of math, you want to write your answer down. Every little step, you want to be writing your answer down and writing the steps down. And here's the reason why. And you can ask, like, I know y'all talk to people that have already gone through this class. You got some upperclassmen friend. Talk to them, and they will tell you how long these problems get. You might spend 5, 10, 15 minutes on just a single problem. And when you get to the end, all they're asking you for is an answer. You go and put your answer in, and they're like, it's wrong, sorry. And if you haven't written anything down, basically you either get it wrong or you just start over. If you've written stuff down, I can come behind or you can come behind. You can look at what you've written down and find that one little problem, because it's probably just one little tiny problem. You fix it, you redo all your math, and it's easy to get to the end by then. And so you need to be able to write stuff down. You need to be able to follow along and have something that I can come and observe what you've done and get to the correct answer. Obviously, sapling, they don't care what you did. They just, do you have the right answer or not? But we're to the point now, and I'm not exaggerating, if you don't know what you're doing, you're not going to be able to figure out how to get to the answer. It's going to be almost impossible. If you follow the steps and go through the stuff that we've kind of taught you, you should be able to get to the end. What this is going to look like, just so I prepare you beforehand, we're going to be doing this thing that we did the other day, our moles to particles, moles to mass conversions, just bigger and more complicated. So we're going back to this type of stuff where we're dividing or multiplying by the molar mass or by Avogadro's number. And we're going to introduce something new today, which is called the mole ratio. Before I get too deep into this, I want to show you again, because I've already done this earlier in the year, but we haven't done it in a little while. So I want to show you again why we're doing the math the way that we're doing it and what we're trying to accomplish. Because once you understand the math part, on some of these science problems, you don't even have to understand what the formula is. You don't need a formula on some of them. You don't need to know really what you're doing. You can just look at your units and figure out just by your units what you need to do. Do I need to divide? Do I need to multiply? Sometimes the units, not all the time, but sometimes just knowing the units can show you what the problem is if you know how this math works. And so, small example real quick, miles per hour. I'm going 30 miles per hour, and I'm going to drive 30 miles per hour for 3 hours. How many miles am I going to go? 90. And everybody knows that because we're familiar with that type of work. But why is it 90? Why did I multiply these instead of divide? Because it's per hour. And so it shows you miles per hour. But specifically, when I make this a problem, how many hours does it take me to go 30 miles? 1. So remember, anything that says per means 1. You're dividing by 1 of those things. So 30 miles per hour is 30 miles divided by 1 hour. That's how long it takes me to go 30 miles. Now, when I set up this problem, what did I do to my 30 miles to get up to 90 miles in my 3 hours? I multiplied, right? So when I'm multiplying, what I'm doing here is I'm multiplying by a conversion factor, and 3 hours needs to go on top. And why is that? Because if I put 3 hours on top, Now I've created a new fraction without any numbers, with just my units. This fraction helps tell me what to do, because if I kind of combine this and get rid of the numbers, what I have here now is miles times hours divided by hours. And so what I have here is I have hours on top and hours on bottom. And anything divided by itself is just equal to 1. And anything times 1 or divided by 1 is just going to be equal to itself, right? And so by putting hours on top and bottom, I've essentially canceled out those units. And the only unit I have left is miles. And so even if this weren't something we're familiar with, miles per hour, I know that if my hours is on bottom of this fraction, per hour, I know it's on bottom, what I have to do to get rid of hours and get into miles is multiply. Now, what if I want to change this? What if I say I'm going 30 miles an hour, but I tell you that I want to go, let me do one that I know will work out, 270 miles. How do I figure out how many hours that's going to take me? I need to divide by, but what do I divide by? So what do I start with?
270 miles.
Yes, and that's the key here, because if I take miles per hour and then divide by, I do my conversion factor, and I put miles on bottom, 270 miles. What I'm doing here is I'm getting a bad fraction, because when I do my units, if I just get rid of the numbers and I do my units, I end up with miles divided by hours times miles, which, if I cancel out my miles, notice that my units aren't in hours. The hours are on bottom. So my units are in per hours, I guess, which doesn't really make sense. That's not what we're looking for. If I do it the other way, if I start with my 270 miles first, 270 miles, put it over 1, and then I do 30. No, wait. If I want to get rid of miles and miles is on top, what am I doing? I'm dividing by my 30 miles per hour, right? So the miles needs to be on bottom. Now they're going to cancel out. So 30 miles per 1 hour. And now when I cancel out my units, miles and miles cancel out. Hours is on top, and that's what I'm looking for. And so sometimes just knowing the units can tell you whether to divide or multiply, and you want to make sure everything's set up right. Now, let's do another problem real quick. Let's do how many seconds in 2 years. So they want me to figure out how many seconds there are in 2 years. Do I know how many seconds are in 1 year? No, but what do I do know about years? 365 days. And if I wanted to do a month step, I can do a month step, but that's just extra work. I know there are 365 days in a year. So how am I going to set this problem up? The only thing they give me in my problem is the number 2 years. And they're asking me for seconds. So they're giving me years. They're asking me for seconds. I need to start with 2 years. And what I'm going to do is divide by 1, just to set this up visually. So I know my 2 years is on top. And as I build out my conversion factors, anything that's on top I multiply, anything that's on bottom I divide. But I know that 1 year has how many days in it? 365. Now, am I multiplying or dividing by 365? I'm going to be actually multiplying because, and here's why. Years is on top here, so I need years to go down to the bottom over here to cancel out. So if I cancel out years on the bottom, I have to have days on top. And I get 365 days in 1 year. Now, how many seconds are in a day? I don't know that, do I? Well, what do I know about days? There's 24 hours in a day. So I can use that. I make another conversion factor. Now I'm in days, and I want to get rid of days. So I know days goes on the bottom. And I know there's 24 hours in 1 day. And then, do I know how many seconds are in an hour? Yeah, not really. And yeah, I could figure it out, but there's one more step to make. What do I know about hours? There's 60 minutes. So I make another one with 60 minutes on top. I want hours on bottom, so it cancels out. 1 hour is 60 minutes. And then the last one I would do, I'd set up for seconds, which I'm running out of room, but I'd have 60 seconds and 1 minute. And what I've done here is I've canceled all my units out. And so if I go back here, years cancels out with years. Days on top cancels out with days on bottom. Hours on top cancels out with hours on bottom. Minutes on top cancels out with minutes on bottom. Seconds is my only unit left. And so when I do all this math, seconds is what my answer is going to be in. And all the math, I'm only dividing by 1 on the bottom, so I don't need to really do any dividing. I'm multiplying on top 2 times 365 times 24 times 60 times 60. And when you get that, that's a bunch of seconds in 2 years. Did anybody do it?
Yeah. 31,500,000. That's in 1 year, huh? No. Yeah.
Is it?
You must have multiplied.
They're arguing. So there's a little bit of debate here. But look, this is what we want to do. And I just want you to keep that in your mind, that if I have a unit on top, or if I'm starting with a unit, hey, focus again. If I have a unit on top or I'm starting with it, I want to divide by the next thing and get rid of it. And so as we take this next step into stoichiometry, we're going to make this a little bit more complicated, because all we've been doing so far, especially if you look at the chart on the other board that I showed you, we've only been converting from one unit to another. So over here, if I tell you I have like 20 grams of carbon, and I ask how many moles or how many particles you have, it's all in carbon, right? I can go from grams of carbon to moles of carbon, and I can go from moles of carbon to particles like atoms, molecules, whatever I'm talking about in that moment. But it's all carbon. And so that's just converting one thing in just different numbers. It's me measuring the same amount of substance with different units. But what if I'm actually doing a chemical reaction? What if I'm taking my carbon and I'm turning it into CO2? It would be important for me to know, hey, if I have this much carbon, how much CO2 can I make? Or if I'm taking this much carbon and I'm making a diamond out of it, how big of a diamond can I create? That's very important, right? So that's what we're missing that step to do. And that's what we're adding today. We're going to talk about the mole ratio. And so if we look at these, the molar mass does what for us? It switches from mass to moles. So I can go from moles to grams or grams to moles. Either way, I either multiply or divide by the molar mass. Avogadro's number gets us from moles to particles. So if I want to know how many of something is in a certain amount of moles, it can tell me that, or go back and forth. Now, mole ratio is going to take us from moles of one chemical to moles of another chemical. And the way we're going to talk about these is chemical A and chemical B. Chemical A is going to be this chemical I start off with. Chemical B is going to be the chemical I finish with. Wake up and put your mask up. Hey, wake up. Wake up. Keep your mask up. Get your piece of scratch paper out. Listen, you can either do it right now or you can do it again next year. I've got plenty of people that come back for a second year. And this is not going to be easy. So you need to be paying attention. You need to be following along on the board and making sure you get this stuff. So what we're introducing right now is actual full stoichiometry. What we've been doing over here is just unit conversion. It's not until you start to switch from chemical to chemical, now we get into stoichiometry. And so this is the full-blown problems. And this is what makes it a little bit harder, because you're switching things up, you're changing your actual chemical as you go along. So stoichiometry is the quantitative. What does quantitative mean? I got numbers, quantities. It can be small, it can also be large. But quantitative means I'm putting numbers to it. So I'm using numbers to describe what I'm doing. So stoichiometry is the quantitative relationship between products and reactants. So now we get to our products and reactants. Reactants is what I put into the beaker. Products is the new thing that comes out. And now I'm doing weight counts and particle counts of all these different things. So this enables me to know the amount of product expected from specific amounts of reactants, and the amount of one reactant needed to fully react with a given amount of product. So think about this. Let's just say, whatever. Let's say these are two different chemicals. They're not, but let me turn around to different. Back of the label, front of the label, two different chemicals. I mix these together, and they have a chemical reaction, and they create something new, right? Is there going to be any of either one of these left over when the chemical reaction is done? You don't know that. You don't know that. And that's actually one of the hardest problems that we're going to end up doing. I don't know, we'll get to it today. They give you an amount of this. They give you an amount of that. You work through both of them to figure out how much of the new product you're going to create. Then you take that answer and work backwards and figure out how much of either one of these is going to be left over. It's a lot of work, and those are the problems that will take you like a good 10 minutes, maybe 15 minutes, and there's a lot of rooms for mistakes there. So if you pay attention and follow the system, it will get a lot easier. If you just want to like wing it, it's going to be pretty tough. So the focus of stoichiometry is this mole ratio between your reactants and your products. Your mole ratios are determined from the coefficients of the balanced chemical equation. So what we need to do first is balance the equation, and that the coefficients here tell us what our ratio is in between these two chemicals. And that's pretty important. Let's see if they give you an example. If not, I'll give you another one. So now actually, this is a good example. We have a balanced chemical equation here. We're taking hydrogen, we're taking oxygen, and we're putting it together to create water. Now, for every amount of water I need, I'm going to need the same amount of hydrogen in moles, right? Because I got 2 moles of hydrogen, we'll make 2 moles of water. But for that same 2 moles of water, I only need 1 mole of oxygen. And so these are different ratios. Oxygen to hydrogen, or oxygen to water, and hydrogen to water are going to be 2 different ratios. They're going to work a little bit differently as we go through these problems. And so now we're getting into very complex problems that require you to kind of think about what you're trying to get done. So what are we doing here? Stoichiometry problems give an amount of at least one substance, usually substance A, in a chemical reaction, and they ask you about the amount of another substance, substance B. To make this easier, we're going to always work from left to right, and we're going to consider us starting at substance A and finishing at substance B. The way the chart works, you can kind of go back and forth, but it's easier if you think of it that way. I'm always starting with A, I'm always ending with B, and I'm going to work from left to right. That's going to help you out quite a bit. So this is your chart. Everybody should have this on the front page of your sheet, and I want you to take a couple notes on this. I'm going to get one for the board, but it's not going to be so big that everybody can read it perfectly all the time. And I want you to have this, so if you go home and have to work on something, you can kind of have this written down. So get a pencil out or a pen, and let's take a couple notes on what we're supposed to do here. Now, I already got my pen. What we're going to do here is we're going to add in what we've been doing on our conversion chart over there to this larger chart, because we're still using a lot of the same stuff. So going from grams to moles of a substance, what do I do to go from grams to moles? I divide by the molar mass. And so that's what I want to write just above this arrow is I'm going to put, I already got my pen set up, a division sign divided by, and I'm going to write molar mass. And just as a reminder, where does everybody get their molar mass from? Periodic table. So you look it up on the periodic table. Now, let's do the bottom one. To go from particles of A to moles. Particles to moles, what do I do? Divide by Avogadro's number. So I need to divide again on the bottom here by Avogadro's number. I'll just write Avo number. So let's go to the other side and see what we got to do. If we're dividing on this side, what are we probably doing on the other side? Multiplying. So going from moles to grams of substance B, what do I do with my molar mass? multiply by the molar mass, multiply molar mass. And I'm noticing now, maybe we didn't need to write molar mass and Avogadro's number here because it's in the arrow, but it's just reinforcing it. So now you'll never ask, what am I supposed to do here? It's there twice. And then at the bottom here, to go from moles to particles, we multiply by Avogadro's number. Multiply by Avo number. So we got divide and multiply. And now the last part, which we haven't really talked about, but this is going to help you out as we go through this. For the mole ratio, write B over A in a fraction. And that's because if we're doing it like we're supposed to, we're always starting somewhere in A and moving to the other side towards B. Your fraction will always be moles of B over moles of A. If you go backwards through it, you got to flip that. It's got to be A over B. But we kind of went over that with our little units example over here. Whatever's on top, if you want to get rid of it, put it on bottom. So if I'm moving from A, trying to get rid of A and going to B, I'm going to put A on bottom, and I'm going to have B on top. That's going to help me do that switch. And so these notes will help you as you start to do some problems. Again, your main goal at the very beginning is to know what numbers are they giving me. So I'm going to start out over here on every single problem. They're either going to give me grams, moles, or particles of my starting chemical. I'm going to start in one of these three boxes, and they're going to ask me for either grams, moles, or particles. And I'm going to have to move through these little yellow arrows. And every time I pass a yellow arrow, I got to do something. If I pass this one, I got to divide by molar mass. If I pass that one, I got to use the mole ratio. If I pass this one, I got to multiply by Avogadro's number. You're always following along this path, starting over there, stopping over here, and this chart will tell you exactly what to do, how to get there. Now, it's going to be kind of complicated. They're not always going to be super easy, but that's where we're starting out at. So let me go back to the PowerPoint. You got your notes on this, and they're going to start with some steps. Step one, I need that balanced equation. For sampling purposes, a lot of time they're just going to give this to you because we got a lot of work to do. We're not trying to reinvent the wheel. They'll give you the balanced equation. So just look and see, does it have any coefficients? If it does, trust that it's balanced. If it doesn't have any coefficients, maybe check it and just do a quick check. Is it balanced? Is it not balanced? You should be good. Step two, write down the number and units given for substance A. And notice they're even telling you now, you need to write this stuff down. If you're just trying to do it in your head, you're not going to get to the right answer. Write down the number they give you where you're starting at. Step three, use that chart to set up your conversion factors all the way from where you start at substance A to where you want to finish at substance B. Step four, the easy part, execute the calculation. Put it in your calculator, hit enter, and find that correct answer. So they go back to this. How many moles of water vapor form when 0.34 moles of oxygen react with hydrogen gas? Assume there's sufficient hydrogen gas to completely react with a given amount of oxygen. So here's what they tell me. Turn the lights on real quick. What do they give me in my problem to start with? 0.34 moles. And what are they asking me to give them back? No. Moles of water. And so make sure you're getting your chemicals right too. They're giving me moles of oxygen gas, and they want to know how many moles of water I have. They're telling me, just so I know, I got an infinite amount of hydrogen gas. I'm not going to run out of hydrogen. I don't have to worry about that. I'm going to use up all of my oxygen, and they want to know how much water I create. So let's go to the board, and let's do this problem using our little chart here. Because this one's going to be a short one. It's going to be pretty easy. Now, do they give me a formula here? They don't, so I need to make my own formula. Most of the time, they're not going to make you do this, but we don't have a formula, so we need it. What am I combining to make water? Oxygen and hydrogen. Is this okay for oxygen and hydrogen? No. Why? They're both on the list of diatomic elements. They can't be by themselves, so it's got to be O2 and H2. And then what are they turning into? H2O water. Is that balanced? No. What do I need to do to balance it? Double my water to even up my oxygens. Now what? double my hydrogen to even out my hydrogens. Now I got a balanced equation. So this is important. What's the coefficient in front of oxygen? How many oxygens do I have?
One.
Just one. So I got two atoms, but moles of O2, there's nothing here, so it's a 1. I have one of these things, and so that's good. So I have coefficients of, I'll write them underneath, 1, 2, and 2. Is everybody okay with that? Those are my coefficients, 1, 2, and 2. So the problem is, I'm starting off with 0.34 moles of oxygen, O2. I'll put it over 1. And what do I need to do if I'm going from moles of A, and they want me to answer in what? Moles of water vapor. So I'm going to moles of B. So A is my starting chemical, it's oxygen. B is my ending chemical, it's water. What is our instructions here to go through the mole ratio? What did I tell you to write down? B over A. And what we're doing here, this is a mole ratio. What is a ratio? It's just a fraction where you can use the colon to do a ratio symbol. But a ratio is just a fraction. And if it's a mole ratio, what's on top and bottom of this fraction? Moles. It's going to be moles on top and bottom. And so that A over or B over A just tells you what you're putting on top and bottom. So what I want here is a fraction with moles of B over moles of A. Now, which one is my starting chemical? Is it oxygen or water? Oxygen. So A is oxygen, O2. B is what? H2O. And yes, what we're going to do is we're going to use these coefficients. So how many moles of oxygen do I have? Just the 1. I have 1 mole of oxygen. And how many moles of water do I have? 2. So what this tells me, 2 moles of hydrogen. So what this tells me, for every 1 mole of water that I put in, I'm going to get 2 moles, or sorry, I said that wrong. For every 1 mole of oxygen that I put in, I'm getting 2 moles of hydrogen out. So I expect my number to double, right? No matter what I have for my oxygen, if I'm putting 1 in, I get 2 out, it's going to double. And so that's what I'm going to see happen over here. When I do this, it's going to be 0.34 times 2. I don't need to divide by 1 because it's not going to change my number. If you want to do it, the calculator is not going to change. It'll still work. So you can divide by 1 on both of these if you want, or you can just multiply 0.34 times 2, and the answer should be 0.68. And your answer is in moles of what? Water, H2O. Okay, and so this one is pretty simple because you can see we only took one step. We used that mole ratio with the coefficient of the number of moles of our ending chemical over top the coefficient of the number of moles of our beginning chemical. And you can see, I forgot to point it out, moles of O2 is my unit here. It's on top. It's going to cancel out with moles of O2 on the bottom here. So this unit's gone, that unit's gone. The only unit I have left is moles of water, which is what I was after. So we will see that they do the exact same thing. They get their balanced equation, which is the same equation we got. They get their starting number, 0.034 moles. They set up their mole ratio, which is 2 moles of water over 1 mole of oxygen, and they use this to convert. And so now I found out that 0.34 moles of oxygen is equal to 0.68 moles of water. Now, you can see this problem could have been longer. They could have gave me grams of oxygen and asked me how many grams of water I would get out. And so in that case, I'd take my grams of oxygen, I would divide by the molar mass to turn my grams of oxygen into moles of oxygen. Specifically, this would be the molar mass of oxygen. Then I use my mole ratio just like I did. Then I would multiply by the molar mass for water instead of oxygen, and I would have how many grams of water I created out of that many grams of oxygen. And so they're probably, if I had to guess, going to do that right now. So yes, let's do one more. When solid sodium metal reacts with bromine liquid, solid sodium bromide is synthesized, how many grams of bromine are needed to fully react with 3.5 grams of sodium in the synthesis of sodium bromide. And so this is actually, now we can still do this. We don't have to go to the end and go back. At a certain point, you'll get to really long problems where you have to go all the way this way and then take your number, switch your chemicals around, and kind of go all the way back. And trust me, they can get very long. This one, I don't think we'll have to do that bad. So right off the bat, let's do another example. Make sure you're taking notes on this. So when we start this assignment, maybe tomorrow, you can follow along and at least have somewhere to start. So let's see. What's our chemical reaction? We got solid sodium. What's the symbol for sodium? Na. Plus, what's our other chemical? Bromine. Br. And they're combining together to form what? Sodium bromide. NaBr. And I got a couple things to think about. Bromine is on the list of diatomic elements, so this has to be a Br2. And sodium is what charge? Find sodium on the periodic table. What charge is it? It's a +1. What's the charge for bromine? -1. So when I put sodium and bromide together, do I need any subscripts? No, because it's a +1, -1. They're going to cancel out. So last thing I need to do now is balance this. So I got 2 BRs over here. I need a second BR over here. I double it, and then 2 in front of my Na. Now I'm doubled. So now I can start my problem. What's the number they give me to start off with? 3.5 grams of sodium, Na. So I'm starting off with grams of sodium. I'm going to put it over 1. Now, what's the first thing I need to do? Well, before I even start on that, where am I starting? Grams of substance A. And what do they want me to go to? How many grams of bromine? So I need to go to grams of substance B. So I'm going all the way from grams of A to grams of B. You know what? Just so this may help out just a little bit. Come back to your chart here, and where you wrote molar mass, write A underneath it. And where you wrote molar mass over here, write B underneath it or next to it.
Avogadro's number?
No, because Avogadro's number is just Avogadro's number. It's not different for any chemical. But your molar mass for chemical A will be different than your molar mass for chemical B. And so you got to know that those are 2 different numbers. Yes?
So like on the modules that you're talking about, will we have to go A to B coming back? Or A over B coming back?
Yes. We're not going to get to those today, so don't worry about that too much. But yes, when you get to the real long problems, basically you got to do this once and then go backwards. On some of the problems, you got to do this 2 or 3 times and then go backwards once. But we're going to take baby steps up to that. Let's not worry about the really big problems today. So, what's my first step I need to do to get from grams of A to moles of A? Divide by the molar mass. What's the molar mass for sodium? Is what? Somebody said? 22.99? 22.99. And notice, I got grams of sodium on top, so when I write my molar mass, I want the grams of sodium to be on bottom so they cancel out. That 22.99 grams of sodium is equal to how many moles? 1 mole. So I got 1 mole of sodium on top. So now I'm in moles of sodium. What's my next step from moles of A? Where am I going next? Mole ratio, and that's going to take me to moles of B. So I need my mole ratio with moles of B over moles of A. So first off, what's my B chemical? What are they asking me to finish in? Bromine. So notice here, they're not even asking me about my product. They're asking me to go from my reactant 1 to reactant 2. So that's a little different. So my moles of bromine that I'm trying to get to are 1, and my moles of sodium that I'm leaving are 2. So when I write this here, moles of sodium is on top, and I want to get rid of it. So moles of sodium goes on bottom. And what I want to get into, moles of bromine go on top. And so that is 1 mole for bromine, 2 moles for sodium. And to be honest, I need to use this full equation. It's going to be Br2. Because when I get my molar mass, it needs to be for 2 Brs instead of just 1. So now I did my mole ratio. What's my last step from moles of B to what? I need to go to grams of B, so what do? Multiply by the molar mass. So here I have moles of Br2 on top. I want to get rid of that. I want my moles of Br2 on bottom. And how much does bromine weigh? So somebody take that and multiply by 2 and tell me what that is. 159.808, and that's grams of Br2 for 1 mole of Br2. So was that the last step I needed to do? Yes. Now let's double check that I did everything right, just visually. Grams of sodium cancels out with grams of sodium. Moles of sodium cancels out with moles of sodium. Moles of bromine cancels out with moles of bromine. And the only unit I'm left with is grams of bromine. My math here. So notice real quick, my molar masses are flipped because one of them I'm dividing, the other one I'm multiplying. So where I divide by the molar mass, the grams are on bottom. Where I multiply by the molar mass, the grams are on top. Does that make sense to everybody? Okay, so as I go through this, my math, I'm always going to start at the left, work to the right. 3.5 divided by 22.9. And if this were me, I'd have all this written down, and I'm going to hit enter after every one. 3.5 divided by 22.9. I'm going to hit enter, write my number in here. Divide by 2. I'm going to hit enter, write my number in here. Times 159.808, hit enter, and that should be my final answer. And I get to the very end, and my units will be grams of bromine. Now, let's make sure that I did this correctly. Pretty sure I did, but so they determined the balance equation, which we got correct. Then they wrote down the numbers of their beginning unit, 3.5 grams of sodium. Then they set up their conversion factors, and they set them up just like we set them up. 1 mole divided by 22.9 grams, 1 over 2 moles, and then 159.808. They have 159.1, that's fine. So they divided by their molar mass, did the mole ratio, multiplied by their molar mass, and they got to the answer of, what'd y'all get? Nobody do it? Just out of curiosity? There you go. Yeah, 12.2. Yeah, and so that is your correct answer there. Do they have any? They do have another one. Look, we're not going to do the last one, but let's just look and see what it is. They tell you solid carbon is exposed to a small amount of oxygen gas, resulting in the synthesis of carbon monoxide gas. How many moles of oxygen must be present to create 7.00 times 10 to the 23 molecules of carbon? So what are they starting me off with here? Well, they're starting me off with molecules. So I'm going to be down here in particles of A. That's my starting block. And what do they want from me? How many moles of oxygen gas must be present? So I'm going to moles of substance B. So this one only has 2 steps. I'm going from particles of substance A. I would divide by Avogadro's number. So take this, divide by Avogadro's number, and then moles to moles, I use my mole ratio from my balanced equation to actually do this. And so that's what they're going to do. They set up their balanced equation. They start with their number of molecules. First step here is going to be divide by Avogadro's number. Second step, use your mole ratio to go from moles of A to moles of B. They're going from carbon monoxide to oxygen gas, which is O2. And so they set all that up. What time is it? It's almost time to go. 35, we got 41. You just automatically say yes. Let's see. Yeah, let us do 1. let's do this one, but let's do it to grams of oxygen. Let's do that just so we got another example to do. And that way we don't have to start on the assignment today. We can start to work on it tomorrow. So, what we're going to do here, we're going to do the same thing. We're going to set up our problem, and we're going to work our way through it. They have carbon, what are we doing? We're putting solid carbon with oxygen gas. So I got C plus O2 goes to, and actually, some of y'all had this problem yesterday on the assignment, and what did it tell you it turned into? Carbon dioxide, but today it's turning into carbon monoxide. Why? Like why? I don't know. Well, we're turning into carbon monoxide, CO, and all we need to do here is balance because we're not balanced out. So I need 2 carbon monoxides and 2 carbons, and that should be my balanced equation. Now, what's my number I'm starting off with? Well, you don't need to tell me that you don't know. You could read it or just be quiet. Yeah, 7.00 times 10 to the 23rd molecules of carbon. So I'm going to put molecules of C. I'm going to put it over 1. And my first step to go from particles of B to moles of B, what do I need to do? Divide by Avogadro's number. So make sure you're using this chart. What we're starting off with, for those of y'all that didn't know, we're starting with molecules of carbon.
So you said B, right?
Huh?
You said molecule B?
Did I say B? Oh, my bad. Well, we're always going to start with A. So my bad if I said B. We're always going to start with A, and our 3 choices for A are grams, moles, and particles. So molecules, it's not grams, it's not moles, it's got to be particles here. We're starting with particles of A. We're going to moles. Well, actually, we're going to go to grams. We're going to go to grams of oxygen over here. So we're going from bottom left corner up to the top right corner. And like you said, the first step is divide by Avogadro's number. So what is Avogadro's number?
6.06 times 10 to the 33rd power.
6.02 times 10 to the 23rd power. And that is particles, or we'll call them molecules. Molecules of carbon. And how many moles is that equal to? 1 mole. So remember, Avogadro's number is equal to 1 mole. So now I've done my conversion from moles, and I've done my conversion from molecules to moles. Next step, what do I need to do? Where am I at now? I'm at moles of A, so I need to do my ratio to moles of B. What's my second chemical that I'm trying to finish in? Oxygen. So I'm going from moles of carbon monoxide to moles of oxygen. So my numbers here are for oxygen and for carbon monoxide, I have a 1 and a 2 respectively. So when I set this up, moles of carbon is on top. I got to get rid of that. So moles of carbon goes to the bottom. What I'm trying to get into goes on top. Moles of oxygen. Moles of O2. Moles of carbon. My numbers here, there's nothing in front of the oxygen, so that's a 1. There's a 2 in front of the carbon, so that's a 2. So for every mole of carbon dioxide I have, I'm going to have a half of a mole of oxygen. Or for every 2 moles of carbon dioxide, I only have 1 of oxygen. So that's going to cut me in half. And then if we were doing the board problem, we would stop here. If we're not, we're going to multiply by the molar mass for O2. And that will be our last step. It'll bring us up to the full answer, and we'll be done. So tomorrow we will start on this assignment. So bring your pens and scratch paper and your brains ready to go.